Hi, my name's Greg Justina, and I'm just making a short video to offer some few words of encouragement to those people out there working on theories about how the brain works, and to relay some of my experiences working on my theory. I like to call it organic cybernetics. This is what it was like for me. I came out of high school with a pretty firm and long held belief that when a neuron fires, a pulse begins down the axon, but only one pulse begins at a time. So essentially, only one neuron fires at a time. About 10 years later, I got hit with this idea that a synaptic pattern. Suppose we take a cubic or a 1 centimeter sphere of brain tissue and we document we stop time and we look at that centimeter of brain tissue and we say we document the location of every molecule in that centimeter sphere, and we run that info through a computer program or something, and it tells us which synapses are active, which aren't active, all various stages of activity. We call this a synaptic pattern. So that's the pattern of activity there is encapsulated in the locations of all these molecules. And the idea was that, okay, could this be a unit of memory, a synaptic pattern? Because looking at how you remember a photo, say you see a photo for the first time in your life, it produces a synaptic pattern that is unique to that photo. And it's a nice pattern. You say, oh, wow, that's a nice photo. Okay, a few minutes later, or the next day, whatever, you see the photo again. And this time, it produces the same pattern, but the pattern has existed before. So now you say, whoa, I've seen that before. So we say that because of this, yeah, this is a unit of memory. And boy, that's a rabbit hole to go down, because that means that the brain has to be able to measure locations of molecules and store that information and access it. Um, so there you go. That really hit me hard. I thought that was a great idea. And to be honest, that's all you need to know. If you have the tools to figure out how the brain works, you're there. Drill down and you'll find it right there. That's a nice thing. Um, Beyond that, I can tell you some stuff about the theory that I got. I don't remember it all, and probably some of this stuff I'm telling you might not be true. I'm not sure. Probably it's true, though. Uh, so here goes. I'll tell you about my theory, what I came up with looking at this problem. The first interesting thing is I don't look at why a neuron fires. I look at what the consequences of the firing are. So I'm sometimes, when I'm visualizing the process, I'm sometimes surprised at which neuron went off. But I say that there's three consequences of a neuron firing. Um, Three parameters, probably weighted equally. The first one's the organic, the neurotransmitters that will encourage or discourage other neurons from firing. That's what we see with microscopes and stuff. That's the organic consequence of firing. There's the sleep cycle or imagination. Uh, there's a pointer, two pointers. Every neuron has two pointers. One from the neuron that fired right before it, and one to the neuron that fired right after it, most recently. And these pointers collectively make up a bunch of loops, various sizes. At any given time, there's a bunch of different loops. And the loop that contains the last neuron that fired is called the power loop. And every neuron is encouraged or discouraged from firing to the degree that it adds neurons to the power loop. And during the daytime, the organic and the memory parameters dominate, and the loops get small during the course of the day. But while you sleep, they grow, and it's nice to have big ones. Okay, so that's the second consequence. The third consequence, this is where it gets dicey, has to do with well, it has to do with measuring the locations of the molecules. So let's introduce what I would call the parlif. It's a sphere. It grows and shrinks in size. It changes direction, can take the whole universe with it, or it can pass through these other spheres one at a time that comprise the universe. It's interesting. Interesting. Wherever it slows down, it's always got half the universe on either side of it. So anyhow, that's what's driving this whole thing. Is this parlif is trying to exist at the same place in space and time as itself. It's attracted to itself. It's trying to exist in the same place in space and time as itself, and that's what's driving this whole thing. So So let's look at what a parlift's doing when uh, so, so, so this is my stickler too, is this is responsible for somehow facilitating this access to memory and stuff and your brain activity. So that's what it's evolved into, say, over the 14.5 billion years, or 4.5 billion years if you take it just from when the sun kind of showed up or whatever, I suppose, or when Earth showed up here. Uh, I'm not sure when the details of when that all that happened, but if you it has to start off there too. Like I get the feeling I can build from the Big Bang to now with just a single parlift flying around, moving all this stuff around, doing all this stuff, maybe. But to do that, you have to ascribe to it something, some clue as to its behavior that you take from what it's doing in modern times, what it's doing right inside your brain. And if you can find the right clue and get the thing started right, it's like shuffling a deck of cards. The whole thing's going to deal itself. Um, so anyhow, I'll show you what it's kind of doing. Let's just hang on. Sorry for this low tech thing. Let's see. Whoa. I have to edit this out. Oh, Christ. There we go. This is how the parlift leaves the neuron and hits these other molecules, and it collects information, and it stacks it up as planes behind the plane where it left from. Like it left from this one plane, and it goes out. Now look at this, the way it bends the space. That's significant because it thinks it's cleaned. It thinks it's done the whole right side of the starting plane there. But because it's bent the space, there's a whole bunch of stuff it misses. Apparently, one of the most recent things I read about this was that I'd written myself was that there's a one of these is sent out from each set. Like there's two sets of neurons, the right set and the left set. And when this happens, all the neurons, say in the right set, send out a parlift. The parlift is making appearances there, I guess, or whatever. This one single parlift that's doing all the everything. Each neuron sends out a parlift, and it's packing up this universe, right? And that's like when I first was working on this theory, I had one set, the right set and the left set, and one eye'd be the thought eye, one eye'd be the memory eye, and the thought eye'd be moving, the memory eye'd be still. Every time a neuron fired, they'd switch roles. So the thought eye would be associated with the set of neurons that's sending out these parlifts and measuring the locations of all these molecules. Once it gets out there, it's like looking out into space, you see, with your eye, and now you're at the edge of the you look and look, and now you're at the edge of the entire universe. It's all black. There's nothing left because you've captured all the mass. That's what you think you've done. And boom, that's where you find the next point in time. And that, I think, like this packs up the universe while your other set of neurons is unpacking its stuff. So what you found is what your other set has unpacked. That's what I think is going on. In any case, that's what the experience is like, looking at it from when you're actually drilling down into it and seeing this thing go. But when after the one set, they've all sent them out. Every neuron has sent them out. One, it jumps a synapse. That right at the end, that bit where you can see the cue. Now that the thing's flopped over, so it's shrinking, so it's going back in time, and that would be like a molecule entering the presynaptic membrane, at a synapse, and you've got that globule thing that's full of little molecules, neurotransmitters, and it hits the surface and breaks open, and the molecules fly out. Well, going backwards in time, a molecule would fly in, and that's like when this thing flops over, and you can see how the structure of the synapse of the organ there mimics the necessities of this, the shape of what's going on there, and it's the same with as the pulse goes down the axon or up the axon, whichever way time's going up, there's rings of molecules that enter and a ring of molecules that leave, and they're right close together, and that facilitates the planting of all the information you've got, because each time you plant one of these planes, it involves a growing and shrinking sphere or a shrinking and growing sphere, whichever way. But it's interesting how the structure of the neurons facilitates the needs of the mechanics of this parlip and its activities. Anyways, uh, so the one neuron that fires, okay, it's found in active synapse, and it flies in the synaptic vestibule or whatever, and now it unpacks the thing. Now what I think happens is each time what I was the way I wrote it, and this is what makes me think it's true, is that each molecule that it unpacks the direction of that plane and it stores it's kind of going down the axon or whatever, there's another neuron that fires in the system, or these are points in time, and this thing you're doing, the new set of planes that you're creating here with the new jump, that this neuron is the one that jumped to that synapse. When it fired, it sent out the parlif. Now it's made the jump, and it's coming back, packing up all these things. It's not packing up the universe anymore. It's now packing it. Uh, I think all the other parlifs are packing their previous trails that they have, and this is actually the pointers. It's what we're looking at here, is that this is the part that goes from the right to the left and the left to the right. This is the part that connects the two lives. Like what I think happened was, yeah, the right set and the left set. This is what happens with multicellular life when it evolves. Is there's a there's two living things here, kind of. It's like we got one from our mom and one from our dad, and it's the pointers that connect the two. And one living thing, it can be growing and shrinking, growing and shrinking. The other living thing can be growing and shrinking, growing and shrinking. But if it doesn't have something that stays here, then it always grows and shrinks to perhaps a different cell body. You know, if it was a one-celled animal, say if it was a cluster of one-celled animals or something. But once you get multicellular animals, now you've got two things, so that one's growing, one's shrinking, and one stays on the part that's outside or something. That's what I think, anyhow. So that's probably when it showed up. The pointers is with multicellular life. And in any case, there's probably more to come. I just wanted to offer some encouragement. It's not as the memory. If it's like this thing, this long string of planes in different directions, and you wonder, how do I deal with this? How does it function? And this gives us, say, some idea of what it looks like, but how does it really function? Say it's attracted to one that exists now, is attracted to a synaptic pattern that existed in the past. Well, what I seem to recall is they're attracted and the whole string folds in half. Or these were not in half, but the two events fold in half, and these two spheres kind of I don't know, they smash into each other and they slam down into the middle. And now that's got you halfway back to where the original event occurred. And then it happens again from that point. Boom, boom. Now you're three quarters of the way back, and then 7/8 of the way back. And so you get back to that original point pretty quick, sort of. That's the way the memory functions, is it keeps moving around. You keep moving around in your memory by getting halfway from where you are to where this other thing, this other sphere that you've now been attracted to or whatever. Um, Yeah, like I say, there's a trick to it when you're trying to get the thing started. Uh, the parlif slows down, leaves a shadow, speeds up, slows down, leaves a shadow, comes back, notices that this shadow is attracted to the first shadow, so somehow it finds a way to create this shadow closer to that one and that one closer to this one, doing this over and over and over, trying to get these things closer together, and it just makes all this mass, and eventually you've got fusion and all this stuff, and it's just still keep trying to do it. Like I say, the trick is to get this thing started with the right footing, and and one more interesting thing I'd like to tell you is that the you know, you worry about visualizing and these tiny neurons and stuff. And sure enough, you do. You have to visualize the whole path, all the way from the Big Bang and right through the evolution of life and the evolution of the process of recognizing the photo, allowing the stimulus to create a synaptic pattern, and then other photos messing with it, and then this pattern repeating and having it kick out the recognition, that's when you've stroked all these consequences just right and you've got it going. Um, yeah, you got to visualize a lot of stuff to do that. But like I say, you look at the consequences and the significant events occur uh, on the scale of a sphere of about 6 or 10 centimeters in diameter. You've got one of them's growing, one of them is shrinking, uh, and there's a bunch of stuff jumping from one to the other. The growing ones trying to stay on the growing ones or whatever. Um, yeah, it's interesting because don't be discouraged by thinking that you have to think that really small things and really big things. I'm telling you that this is might be connected with the idea the only place a sphere can exist is with half the universe on either side, and there are no actually small ones or big ones. And the really the toughest thing about this entire exercise is it's almost like the acceptance that the reality really is so different than it appears. It's really hard to let go of what you're looking at and realizing that it's not what it appears. This is just, it's somehow, I hate to say it, some kind of illusion or something, but it's not. It's because of course it isn't. It's very real, you know. Yes, it's very real, of course, but that's the toughest thing, I guess, of the whole thing. Anyways, best of luck to you all, and I'm sure it won't be any time at all before the next slew of successful researchers is upon us. Thank you very much. Goodbye.